Hello everyone, my name is Talha, and today I'll be presenting Learning to See in the Dark. This was published in CVPR 2018. So they're basically addressing the problem of extreme low light imaging. Is it possible to take very accurate images in low light? The problem that usually occurs when you're doing that with current cameras is that it leads to a very low SNR, that's a signal to noise ratio. So what that basically means is that the signal and the noise are sort of mixed in a specific proportion. And if that gets too much in favor of the noise, then the image is not discernible. So as an example, we can see that this is specifically an example from fluorescence microscopy. We start with an SNR of 23, which means that there's a 23:1 ratio for the actual signal to the noise. And that results in a very accurate image. If we start decreasing the SNR, we start noticing that the noise is able to compensate for its version. And eventually we cannot discern the scene at all, and we don't know what's going on. So that gets very close to SNR 1.05. That's when they're occurring in a 1-to-1 ratio. And there are many techniques that can actually be applied to denoise the image, and we're going to start talking about some of them. So in this related work section, let's talk about some image denoising techniques. I'll briefly talk about them here and then discuss them before we talk about the results. So one is the traditional pipeline, in which there are some examples of post-processing techniques that are applied that include demosaicing and white balance and others. And it's basically not a learning-based pipeline, but it's still one of the best ones out there. Another is known as the burst alignment technique pipeline, in which we talk about bursts of images. There are collections of images, and we use all of those images to try to remove noise from our target image. And finally, it's BM3D, which is an important traditional pipeline that they use as for denoising in their results. So the problems with these traditional pipelines is that their performance is really good, but it's on synthetic data, and they don't work on real data. And one of the biggest problems with learning-based approaches is that use deep neural networks is that it is barely able to approach the results of conventional techniques. And another problem that is really important is the lack of ground truth images. So you have images that are taken in low light, but what about images that would serve as ground truth for those low light images? There would be regularly lit images. So what about those? Those are known as properly exposed images. Another category of related work is known as low light image enhancement. It's basically not us trying to remove the noise from images. It's us trying to change the contrast so the image looks discernible. And for that, histogram equalization is a technique that's used. We take the original image. We know that its contrast is not very accurate, and it kind of looks like this in its original histogram form, where this represents the intensity, and that's the number of occurrences. So the histogram is transformed in such a way that we get this image that has better contrast, and we can see the histogram values sort of arranged in a different way now. Another thing that they talk about is gamma correction. So this is a specific example of that. We notice that in this scene, the blacks are not exactly visible. Only some parts of the image close to the white spots are. So when you apply gamma correction, you are able to increase the amplification of the black spots, while at the same time not work too much on the light spots. So over here we can notice some difference between the brightness change, but as it turns out, the rest of the image is now discernible. And that's what gamma correction is usually used for. The problems with these approaches is that noise is not explicitly modeled in their pipeline, and the images are obviously assumed to have a discernible scene. So for example, if we look at this image, we know what's going on, at least from a basic standpoint. And then extreme low light imagery is not going to work. Finally, there are a lot of noisy image data sets that are introduced that have original images, and you add noise to them and then use them in your method. But the problem with these is that most of the data sets are captured during the day, and that does not apply to low light imaging, and that's obviously something we need to focus on. Before proceeding with the actual network details, let's talk about ISO. It's an important term that's used throughout this paper. It represents the range of light that is digitized. So basically, it's something that's inherent of a sensor. After you get a sensor data, you need to apply specific gain to it. You have the option to do that. And once that happens, you have the option to affect the range of the pixels that you want to deal with. So a higher ISO results in small ranges, and that leads to more precise values. What that basically means is if I want to record values between 1 to 10, I could either choose 0.1 as an increment or 0.01. So a higher ISO means that I can go with 0.01 increments and get more values in the range, versus a lower ISO, which would mean bigger jumps. Initially, this looks like a very good strategy, but if you increase it too much, the result is noise and color bias. Let's take an example. That's a low ISO image. We can't really tell a lot at this level, and that's a high ISO image. So we notice some difference in the brightness, right? But let's try to zoom in and see what's going on. So if we zoom in the low ISO image, we can see that it's still discernible, whereas noise has been added to the high ISO image. And it keeps getting worse. This is not a major increase in the ISO. So when we try to increase it by large amounts, we get worse results. So is there anything that we can do as photographers on our end to change the camera configuration and deal with this issue? So let's talk about that. One important thing that people do is change the aperture size. If we have a larger aperture size, then we can allow more light to enter. And when more light is allowed to enter, then the low light imaging would benefit from that. But as it turns out, if we increase it too much, then we end up with depth of field issues and we get blur backgrounds. Also, for large aperture sizes, we would want bigger cameras, and that's not exactly practical. Another issue is known as exposure time. So that's controlled using the shutter speed. So a smaller shutter speed would mean that less light is allowed in at time in increments. And if we try to increase this time, then more light is going to be allowed to pass through and expose the image. But the problem is, if we increase it to a great amount, and there is motion in the scene, then we will end up with there being blurriness, because it's not a static scene anymore. And any amount of activity will affect the result. And finally, if we increase the ISO too much, we notice that the initial results are good, but at up to a certain point, and we get very noisy images. So now we can finally talk about the problem description, which is basically using deep learning or a data-driven approach to achieve low light imaging. I would ideally want to start with a short exposure image that's recorded in very low light. And then if that is the input, I would want a long exposure image or an image that looks bright. So that's what a short exposure image will look like. Let's call it SEI. And that's the result that I would want. We can see that there's not much information visible here, but that is still the result we would want in our situation. So the contributions of this paper are twofold. You use an end-to-end trainable network to enable images captured in low light to be converted to properly exposed images. And finally, they introduce a novel data set, See in the Dark, that consists of SEIs paired with reference LEIs. Let's talk about the data set a little. So it consists of about 5,000 raw short exposure images, and each of these short exposure images are linked with a reference image that serves as the ground truth. So in this case, this particular scene has still been recorded in low light, but because of the various settings, it appears to be brightly lit. And that serves as the reference image. The image that you see in the background over here, that's basically just a black image. That's the short exposure image. An interesting thing is that they actually don't record one single short exposure image and a reference image. They record bursts, so collection of images. And for those collections, there would be one reference image. An important term that they refer to in the paper is known as luminance. Its SI unit is lux. It's basically telling us the amount of light that's hitting per unit area. And it's something that can be controlled in a lot of situations, but sometimes it cannot. For outdoor scenes, it varies from 0.2 to 5. And that's because it's going to be higher than indoor scenes because there's other sources of light we have no control over. That includes moonlight or traffic lights for other examples. And for indoor scenes, they usually end up using just candles, and they place them at different positions. We'll talk more about that in a sec. So exposure time is varied between 1/30th of a second to 1/10th of a second. That's the time the camera is allowed to take light in through the sensor. And the ground truth is going to be 30 to 10 times more than that, which is 10 to 30 seconds. The Fuji images captured by the Fuji camera are going to be 6,000 by 4,000 pixels, and Sony images will be 4240 by 232 pixels. We can now talk about the camera setup, just briefly. So there are two different cameras that are used, and they're assembled using tripods, Sony and Fujifilm. So this is the case for Sony. So there's only going to be one camera that records the scene. So here you can see the light source, which is going to be in the form of candles. That's the light meter that's used to adjust the lux So they want to make sure they have the right value of light intensity, so that's used for that. And then this is the scene that they're trying to capture. So first they try to catch the reference image. So they give like 10 to 30 seconds of exposure time. And then they use an app to signal the change to the camera. So what happens is they don't want to touch the camera between taking consecutive images. So for 10 to 30 seconds, they take the reference image, and then they give it a signal, and then bursts are recorded. And the exposure time is changed, obviously. So the long exposure image would look like this, as you can see from the previous slide. And that was for about 1/2 of a second, I believe. And the burst image would look something like this. That's for 1/30th of a second. Another important term is amplification factor. We'll refer to it later on in the pipeline. It's when we're trying to increase the brightness of the image. From left to right, you can observe the amplification factor gamma increasing, and so is the brightness. So when we talk about sensors, there's a specific component within them that's responsible for capturing the scene, or for the photograph we end up getting in our phones. So basically, these filters allow specific colors to pass through. So this is our sensor in question. This part of the sensor is equipped with a filter that only allows red light to pass through. So we end up with a checkerboard pattern for the color red. And the same applies for the color green and blue as well. Once we obtain these different checkerboard patterns, it turns out that the white pixels over here have no color. Only the red pixels that you can see have the color red. It's not going to be a regular RGB channel. It's a color assigned to a specific pixel. So when you end up merging all these three results together, you end up with a checkerboard pattern like that. And that's going to be my image in its raw form. And you can see there's another important thing that you can notice over here. There are twice as many green pixels as there are red or blue. The reason for that is because humans are more susceptible to the color green. Our eyes are more sensitive. So that's sort of incorporated in the design. Demosaicing is basically the process of converting these RGB filters to an actual RGB image. Bayer is one specific kind of filter. So they wanted to check if their method can actually extend to two different kinds of filters. So they apply another one. This is what Bayer looks like. That's our RGB image. And the only difference between our X-trans is that there's a block of 2x2 greens instead of just 1x1. So it's just a different arrangement of pixels. It achieves the same purpose. We can finally talk about the network architecture. So ideally, we're starting with a short exposure image, SEI. It's dark. And we would like to pass that to a convolutional neural network and get our predicted output in the form of LEI prime, which is the predicted long exposure image. We want that specific image to be approximately equal to our ground truth, which is just LEI. And we do that via the L1 loss. So it's going to be LE prime minus LEI and the absolute value of that. So let's talk about it in terms of the raw sensor data that we're talking about. So they're not processing RGB images, but they're processing sensor data. So the pipeline would sort of end up looking like this. We start with the bare raw image of height by width by 1, and then we basically pack that into 4 specific channels. So we're going to pick the red pixels from here, convert that to one channel, the greens, convert that to one channel, and then repeat the process until we have H by 2 by W by 2 by 4. So it's 4 channels, but we've reduced the dimensions in a sense, and that's the motivation behind it. We basically want to reduce the dimension. The next process is that we try to subtract the black level from these filters. As you can see in this particular image, it just has, its black level is higher than this specific image. We don't really want too much black in our image, or we don't want a lack of it either. So there's an optimal level that needs to be maintained so we can look at the background and observe the color changes. So this black level has to be extracted first. And then an amplification ratio is applied, which we talked about earlier. It's when we try to increase the brightness. And it's no coincidence that they're doing this in a sequential order. They're trying to remove the black level first before amplifying the image. And the reason for that is if they amplify it without deducting the black level, the black parts of the image are going to be amplified as well, leading to a worse image. The result is passed to a convolutional neural network, and the result of that would be 12 filters of the size H by 2 by W by 2, and those would be then arranged via another process that I'm going to talk about, and the final RGB result is going to be presented. So what do they use for their ConvNet block? Their motivation lies in using UNet, which is basically an encoder-decoder architecture, but with skip connections. So let's just talk about how that's going to look like. So we start with our image, our 4 channels from the previous slide, and we would want to apply a 3x3 convolution on that. Okay. We start with our filters, 4, and the first step would be to do a series of convolutions. And it's going to be a 3x3 convolution followed by a leaky ReLU activation. So 32 filters are going to be generated from this, and then 32 filters will again be generated from that. When I'm done with this result, my next job is to use the max pooling. So when I try to max pool, I will reduce the dimension in a way. And when I reduce the dimension, it's going to be still 32 filters, but with a reduced dimension. After that, I will increase the number of filters from 32 to 64 and apply the same process again. So from this point on, I'll get 64 filters for this, and I'll then stick to this. So 2 convolutions of 64 filters, followed by another max pool. I get 64 filters of reduced dimension, and then I apply a couple of more convolutions. So I'm basically I'm doubling the number of filters at each layer. And if I apply another convolution, it's going to be this. And I'll keep on increasing the number of filters, max pool, until I finally have 512 filters with the dimension being minimized in this case. So you guys might be thinking like it's kind of like similar to a conventional encoder-decoder, but there's a big difference that we're just going to talk about. So we take these 512 filters, and we are going to upsample and concatenate them. So here, there are 2 different processes that are going on. We take these 512 filters, and we make them go through a deconvolution. It's not exactly a deconvolution. It's known as a 2D convolution transpose. So what's happening is we take these 512 images, and we are going to increase their dimension. And once we do that, we will get 256 filters from here. Because once we're applying the deconvolution, we'll be getting 256 out of those by choice. When we have those 256 filters, we will take the result from the previous layer that we had obtained. So the feature maps of this layer are going to be appended to our deconvolution results from this layer. The intuition behind it is that we want to capture the fine-grained features of the image, so we append these both different level features together. After that process, I will generate 256 filters and apply a 3x3 convolution again. And basically, it's going to be 2 successive convolutions. After that, I will apply the up convolution process again. So out of these 256, 128 filters will be taken, and they will be appended from the 128 filters from this level. So as you can see, we are sort of getting a U-shaped network with skip connections. And that's their motivation. We eventually get 64. We eventually end up getting 64 filters over here, and then we go through 2 successive convolutions again, so that we have 32 filters, the filters we actually started with. And then finally, we will do a 1x1 convolution with no activation, and end up getting H by 2 by W by 2 by 12 filters. So these 12 activation maps are not in the form that we want them to be. So what do we do after that? So we have the result from the ConvNet. We would want to convert that to an RGB image. There was a CVPR paper published some time ago that talks about the idea of a subpixel layer that takes low resolution images like the ones we have and convert them to a high resolution image with great accuracy. So they use that as their specific code to achieve this process. So now I believe we can talk about the training process and how it was used. So the raw sensor data is used in the training process versus sRGB. We've talked about that. Our RGB images are not used in this paper. They are at a point, but they're not giving the optimal results. So our data set was basically collected like that. So we have 2 different cameras, Sony and Fujifilm. These represent X300, X250, and X100 represent the amplification ratios, how bright we want the images to be. And the 2 filter arrays are bare and extrons. So a different camera would most definitely have a different filter. So that was their choice. And the exposure times are varied for both of these. And we end up getting about 5,000 images. About 70% of each row is considered to be the training, and 20% is the testing, and the rest is the validation. They apply data augmentation as well. At runtime, they extract random patches from the images and apply random flips and crops to them. So I think we're at a time that we can talk about the evaluation part. So they perform 3 specific experimental evaluations. For the first part, they compared their result to traditional pipelines and see if their approach is better. And in this particular case, BM3D and burst denoising is used. We'll talk about that in 1 second. For their second experiment, they're trying to test cross-sensor generalization, which is if their approach is independent of that. So instead of trying their camera sensors from Sony and Fujifilm, they try an iPhone 6s and they see if their results are still good. Finally, in experiment 3, they change the components of their specific network and observe any changes that result. So experiment 1A was perceptual. They hired Amazon Mechanical Turk workers to check whether the images were of better quality or not. And the 3 methods that were used were BM3D, burst, or the proposed method. About 1,180 comparisons were carried out by 10 AMT workers. And these are their results. So X300 represents brighter images and X100 doesn't. So they basically got their results better on the brighter images, which as they claim is more challenging. But when it was the darker images, and the AMT results proved to be less accurate in that sense. So let's talk a little about the baseline methods that are used over here. This is just a traditional pipeline. We can briefly talk about it. So we take our raw sensor data that we have for our images. We make it go through a white balance and demosaicing process. And then we basically just denoise and sharpen the image, followed by color space conversion and gamma correction until we have our output. We've talked about some of these techniques, but the bottom line is that it's just a collection of post-processing techniques that was used. The burst denoising method is different in the sense that they consider a group of images, and it's still raw sensor data, and they use each of the images. The intuition is that you use each of the images to make sure that the noise is removed from the image. So you have more information in this case, and it still gives them better results. The BM3D transform domain filtering. This was another baseline that's used in their paper. What ends up happening in this is that there's a block matching algorithm. You have a very noisy image. So you take a reference and try to find other patches that are close to that reference you're talking about. Then you make that you input that reference R through a pipeline of 3D transforms and then recover that reference. So you're recovering the image patch here. And they were able to get very good results with that. So this is by default the best traditional pipeline that was present, which is why the authors ended up using it. So the qualitative comparison for the traditional pipeline was this. We start with an image that's produced by the camera. It's a clarification that's required here is this image is not actually used during the pipeline. It's just for our sake to demonstrate the results. Both of these pipelines end up using raw sensor data. So the raw data is processed via the traditional pipeline. We can see that if we zoom into these regions, there's not only color bias, but the noise is increased a lot versus their result. And when we zoom into these parts, we can see that the color conversion is actually very good compared to this case. Then they apply the same idea to BM3D. So they have this traditional pipeline. Again, noise is being generated. But then on top of this pipeline, they pass the result from A to BM3D. So when they do that, they end up getting good results. And that was predicted because BM3D is a very good denoiser. But when they compare it to their results, they were getting slightly better results. As you can see, there's noise observed to be here, even though most of it is removed over here. But still, if we compare it to this case, it's still better. So we can talk about experiment 2 now, when they wanted to test different sensors. So the idea was they wanted to experiment if images captured by different devices will give good results. So iPhone 6 images are tested. That's the traditional pipeline being applied to an iPhone image that was captured in low light. And that was their result. And as you can see, there's a very huge difference between these results. So the evaluation metrics that are used for subsequent experiments are PSNR. You attempt to find the signal-to-noise ratio, and that basically depends on the mean square error that you find between the image that is generated and the reference image. So the higher the value, the better it is, because we want the signal to be dominant than the noise present. Another metric that's used is known as structure similarity. So structure similarity takes two images and finds the relationship between L, C, and S in a product form, where L, C, and S represent the luminance, contrast, as well as the structure. So it's sort of demonstrating how close X and Y are in terms of luminance, contrast, and structure. So it's not just one value, they're considering all three of these properties. So let's see what their quantitative results look like. So they started replacing specific components and analyzed the change. So their default pipeline gave a result of 28.88. That's a PSNR, so that's the highest value they got. And this is the structural similarity. And for the Fuji, we can observe it has dropped. They replaced UNet with another architecture that's known as context aggregation network. And basically, after using it, they were still not able to get very good results, but their motivation was they wanted to try different components. So for this paper, they operated on raw sensor data, right? When they switched to regular RGB images, their performance dropped significantly, as we can observe over here. They tried different losses. Only a few of them are mentioned over here, but the best loss was turning out to be just L1. When they replaced that with the structural similarity loss, they were getting good results, which were close to the default pipeline. As you can see, the structural similarity over here is higher than the default pipeline. But as it turns out, they made the case that some of the colors weren't accurately reconstructed in the process if they used this specific loss. So they did a qualitative comparison. When L1 was replaced with L2 loss, there was not a significant improvement, so they decided to go with L1. So the representation that we talked about in the Sony camera, which was in the form of a Bayer array, right? So there's two different versions of the Bayer array that you can use. The packed version is when we convert them to 4 different filters, like we did in the slides. The other version is we apply a mask. So they just wanted to see if a change in representation would affect the performance, and it did not. It reduced it. And you can see that they obtained no results for Fuji. The reason is the Bayer array is only present in the Sony camera. So they wanted to test something related to the X-trans as well. So the Fuji consists of the X-trans array. So usually how data is arranged is in 6 by 6 blocks. So, but they went with 3 by 3 because of various reasons that are not specifically mentioned in the paper. And when they converted from 3 by 3 to 6 by 6, they noticed no significant improvement over the default pipeline. Stretched references are generated using histogram stretching. It's a process that they wanted to incorporate in their original pipeline. When they use histogram stretching, it turns out that the network gives very bad results. But when they apply histogram stretching as a post-processing technique, once they obtain their original results after like UNet or default pipeline, that seems to be giving them better results compared to this. So they eliminate that from the pipeline. So the conclusion of this paper is that the authors propose a deep learning network to solve the problem of low light imaging. And they are able to achieve results better than traditional and very recent denoising pipelines that include BM3D. And they try a combination of different components as part of their network, but UNet and their default pipeline is able to outperform every single one. In addition to that, they introduce a novel data set that is catered specifically to solve the problem of low light imaging. Some ending remarks. The proposed pipeline does not work for motion in images. The images have to be static. So in the related work section, they criticize a lot of other papers for their techniques not being able to work efficiently when there's a dynamic scene, when you have moving objects. But it turns out that their method is not working for that either. It has to be all of their cameras, the camera setup had to be in such a way that everything was static in the room. The pipeline is also not efficient for real-time video capture, which was one of their initial goals. So the time it takes to generate an image in real time has to be much lower than their result right now, which is between 0.3 to 0.6 seconds. Finally, in my opinion, the cross-sensor generalization is not well tested in this paper. They just took an iPhone 6s and they were able to get good results with that, but they didn't test enough sensors to be able to make that statement. And interestingly, the iPhone 6s they used consisted of the bare array. So that was a problem. And finally, during their data collection, a lot of settings had to be optimized. So it's really impractical to be collecting a large data set because you need to adjust ISO, aperture, and focal length when you're recording each scene differently. And that's it.